Hello everyone, welcome to my channel Predicting the Future. Today we are gonna talk about math. We're gonna talk about statistics. We're gonna talk about data science, the machine learning, whatever it is called. We're gonna solve real problems, a problem that is very commonly available in many fields of industry. And smash the like button for the YouTube algorithm. What is the problem? Look at the graph here. This is the data we collected. How can we tell? What information we can extract from here? It looks like a two bump from two different data sets, isn't it? Well, your instinct is very likely true. But how do we describe the model? What class of data, which part of data is more likely from one distribution rather than from the other distribution? Right? So we have to find a math model to fit into our data set. And from there we need to estimate the unknown parameters of these two distributions. With those estimations, we can fit the data sets into a mathematical model. We can figure out whatever the probabilities we want to extract from this data set. For example, what is the probability of a sample that is from distribution 1 on the left side, and what's the probability that this sample is from the other distribution? So this is what we were gonna do. So we are going to talk about an algorithm. This algorithm is called EM algorithm. The full name is expectation maximization algorithm. It's based on the basic knowledge about maximum likelihood estimation. So let's describe the problem here. So what problems do we have? So we see we have a sample. We believe this sample, let's say this sample is called X. There's n samples from x1 to xn. They're all identical samples from a common probability density function f, and the parameter we need to estimate is called theta. However, there's some hidden information we don't know. We call it z. What is the hidden information I'm talking about? The hidden information is given a sample, what's the probability that this sample is from the left distribution rather than from the right distribution. So this is an example of hidden information or hidden data set. We don't know that. So the PDF of f, what it looks like, how do we find it? Usually when we look at our data set, we have some ideas. We'll assume something, right? We assume it fits certain model. Here, I'm assuming this fits a Gaussian model, a Gaussian mixture model. So this X sample we observe, I'm assuming that this sample is coming from distribution, a Gaussian distribution with mean vector mu1 and covariance matrix sigma 1, when z, the hidden information, is 1. So what does this mean? So this a hidden random variable. If the random variable is 1, then the sample is from the distribution from this smaller bump. If z equal to 2, the distribution is from the right side. So this is z. This is hidden in the sample we observed. We can't get this actual value for each sample. This is hidden. So how do we find the probability density function of x? It's quite easy, right? So, well, it's quite easy if we understand that. So so we assume that z, the probability of z equal to 1 is tau 1, otherwise it's 1 minus tau 1. and the parameters we are trying to estimate from the given data is this vector, or this vector of something. So first we need to estimate tau, what's the probability of tau 1 and tau 2, and mu 1, mu 2, sigma 1 and sigma 2. This is what we need to find. This is the final estimation we need to find. So what is the PDF of x? Now the PDF of x can be calculated easily by taking the derivative of cumulative distribution function. So the probability of x less than equal to x is actually equal to, based on the Bayesian rule, is given the conditional probability of z equal to 1, x less than or equal to x, times the probability of z equal to 1, plus when z equal to 2 and x less than or equal to x, times probability of z equal to 2. And once we take the derivative of x, we get tau 1, which is from this one, tau 2 is from this one. This is tau 2. And when we take the distribution, when we take the derivative of the conditional distribution, what it looks, how do we get that? So we know that when z equal to 1, this x is from this normal distribution, this Gaussian distribution. So the PDF of this Gaussian distribution is f. This is not the same f. This is this f here. This f here is the Gaussian probability density function. I shouldn't use this same symbol. So the whole thing here, the whole equation in here, is the probability density function of the sample x. Now let's go back to our problem. So this is z. This is what z means. So now we have known sample, we have hidden sample, and let's define a drawn PDF of x, which is to be g. This is a drawn PDF of x. What does g look like in Gaussian model? Let's look at that. So g is called incomplete likelihood function. It's a product because the sample x are all independent. So the drawn PDF of x is actually density function we already calculated from here. So right. So this is what we found for a single x. For a sample of x, that will be a product of the density function because they are independent and identical. So this is the g function we are talking about, the g function here. What is h? H is the complete PDF of x and z, which is the drawn PDF of x and z. And let's define k, a function k, which is a conditional PDF given x and theta. It's a conditional PDF of z given x and theta. So by Bayesian rule, given the sample x, we know the sample x, what is the probability of, and theta, what is the probability of z, can be written by Bayesian rule h divided by g. So for those who don't, if you don't understand this, please comment on in the YouTube video, and I will explain that in a separate video. We want to find the estimate of the unknown parameter theta. So we will conduct a maximum likelihood maximization to maximize the probability of x by maximizing the incomplete density function g. So how do we do that? So McLachlan and Krishman has a in-depth knowledge of this EM algorithm, which is written in their books for the book in 1997. So let's see how the EM algorithm works. So the EM algorithm is trying to, what the EM algorithm is trying to do? The EM algorithm is trying to find the point estimates of those unknown parameters theta by maximizing the probability of observing this exact sample we see. We're trying to maximize this probability. What is the probability? This is, well, if the probability, if this is a continuous density function, then this is a trying to maximize the probability of this instantaneous probability of observing exactly those samples. If it's a discrete random variable, that would be the probability of observing those specific values. So we're trying to maximize that by finding the value that maximizes the function g. It's the same of maximizing the log of g. So the log of g, what is that? It's a log of g. We integrate that with a conditional PDF z given theta 0 and x. And without log g, this is just 1, right? This is just a probability of 1. You're integrating everything of the PDF with respect to z. That's the definition of probability density function. So g we can write as a function g can be write as h divided by k. When we take the log, that will become minus the log of h minus the log of k, and times k function integrate with z. We separate them, and that will become two components. The first one is expectation of z on the log of h given the conditional expectation of z given theta 0 and x on log h minus expectation of z condition on theta 0 and x of log k, log of function PDF k. So what is theta 0? Theta 0 is, so EM algorithm is an iterative algorithm. So we're gonna gradually, it's like the Newton method. We're gonna gradually find closer and closer to the best value of theta that maximize this function. Same here. So given any initial theta 0, we'll find a better theta, and then given this another theta, plugging the theta 0 becomes the same next theta 0, you find another better theta. So this is the fundamental idea of EM algorithm. So here I'm going to introduce two terms. One is called incomplete likelihood function, which is actually the function g, the PDF of g, and a complete likelihood function, which is function h, which is the joint PDF of x and z. So we also let's define. So now we comes to these two terms, these two expectations. The first expectation minus the second expectation, and we are trying to maximize this thing. How do we maximize that? The idea is the bigger the first term, the smaller the second term, then the bigger value of this function, log function, right? So we want to have the first term bigger and bigger, the second term smaller and smaller. So let's define the first term. Let's give a simple idea. It's too long. Let's give a simple function, and let's define that as a function q. And the second term, let's define that as function r. What is the algorithm? There's 3 steps. The first step is we calculate the expectation, which is we calculate the expectation of q, and then we maximize q. We've tried to maximize q, find the next theta, we call theta m plus 1, to maximize q, and then we'll take another theta m plus 1, plug into the e step, and then try to find the maximized value of theta m plus 2 given theta m plus 1. and iterate. It's similar to the Newton method. We're going to find closer and closer x value to get the maximum value of the function. And how do we stop that? So when we use computers, there will be errors, there will be numerical things we have to be careful. So if the value of q were given theta m on theta m plus 1 minus the previous m q value of given theta m is less than a certain threshold, we're going to stop. So that's a condition when we stop it. And you might be curious why we only maximize the first term, not minimizing the second term. So why only maximize function q but not minimize function r? There's a theorem we can prove that given the theta m and the theta m plus 1 we calculate in here, the r term of the theta m plus 1 is actually less than the previous r given r value of theta m. That is, for our next iteration for the theta, the first term becomes larger and the second term becomes smaller. So we only need to maximize the first term, and naturally the second term will become smaller. This is easily provable using Gaussian inequalities. Let's try that here. So we need to prove this is the definition of R. We need to prove expectation of z given theta m x of log function k minus expectation of z given theta m x log function k on theta m. So, and we need to prove that this is less than or equal to 0. We just move around the whole thing and move the terms inside expectation because of the log becomes so we get one term that is the log of kz given theta m plus 1 divided by kz given theta m. And so the log is inside the expectation by the Gaussian inequality. We take the log out, and that is the Gaussian inequality. The first term is less than the second by moving the log function out of the expectation. And then what is inside here is just it's just a function of log of 1. So the term function k is cancelled out. This two cancel, and they become integral of the PDF, and that's just 1. So we get 0. So we prove that the next iteration theta m plus 1, the r term will become less and smaller and smaller. Now, so this is the EM algorithm. And now we can go back to our Gaussian model. So we already found our incomplete likelihood function L given theta and x, and we can find our complete likelihood function L given theta x and z, which is a product of the sample x and z. Well, z depends on if the value is z is 1 or 2. We're gonna pick whether the density function is the first normal distribution or the second normal distribution. So the I here is identity random variable. That is, if the z are equal to j, then this is 1. If the zi random variable, the observation of the zi is j, then this is 1. Otherwise, this is 0. So this is just a product of each individual PDF of the sample x and z. So to simplify, we can take the, because it's too complicated here, we can't calculate easy. We can just take the we can just take the take the exponential and take the log function of the whole thing, and then take another exponential. That will cancel out. It's the same function. Now we can take out the random identity random variable out as a time, and then take the log. So inside of here, it's just the Gaussian PDF. You can go to Wikipedia to find out the Gaussian the multivariate Gaussian PDF, what it looks like. When you take the log, you get, and take the exponential, you get the whole term defined in here. Now we have our incomplete likelihood function. We have the complete likelihood function. There's one more thing we need. What do we need? Let's go back to our algorithm. So we see we need to find value. We need to calculate Q, which is expectation of Z upon given the condition of theta and X, which is we need. What does it mean? We need the PDF of Z given theta and X. So we need that function in order to calculate this Q. We already have this log of H. The log of H is just the log of the complete likelihood function. So how do we get this function K? The function K is the probability of Z given X and theta, which is probability of, let's say, Zi equal to J is 1 or 2, given Xi equal to Xi, which is the observed value we have, and given the theta, the initial theta value, or the next iteration theta value. So that's the PDF. Z is a discrete random variable, so this is the PMF. Same thing, we're gonna use Bayesian rules. So that will be the probability of Z. So here, this the first term, the numerator here is the probability of Z equal to J and Xi equal to Xi and theta equal to theta t. This is the John PDF of Z, X, and theta. Divide by the probability of Xi equal to Xi and theta equals to theta t. And this is the incomplete likelihood, and this is the incomplete the John PDF, which is the function g. So we already have that in here. The function g is here. We already calculated that. So this is the numerator. Now, how do we get this is the denominator? How do we get this numerator? So this is the probability of Z equal to J and Xi equal to Xi and theta equal to theta t is the same. We apply another Bayesian rule. Will be the probability of Xi equal to X, theta equal to J, given Zi equal to J, and that will be this one or this one times the probability of Z equal to J, which is what we are doing is we are actually using these similar Bayesian rules here. And then we got the value of tau J times the PDF of Gaussian distribution. So you see here, this is this is calculated mathematically, but intuitively you can see the probability of the sample is from Z equal to J is actually the proportion of these two terms. You see these two terms plus together is actually one of the terms. So that's very intuitively calculated, but we just calculate that. Well, I didn't write it down, but this is how we calculate this probability function. So if you still need some explanations here, please comment and I will explain that in a separate video as well. And subscribe to my channel, Predicting the Future. So now we got the PDF the K function. Now we can calculate Q. The Q is just a conditional expectation of z given x and theta t on log of the complete likelihood function. We plug in the function, we plug in those functions we got, and and then that becomes the expectation, and the expectation of so this is this part. So this one, the probability of zj is just the k function times the expectation term, which is the log of L. And then we will get a term like this. So this is the function Q, and we need to maximize that. So we need to maximize the whole thing here, which is the Q function. It seems like complicated, but it's actually not. If you look at the term, it's actually separate. You see the tau term and the covariance matrix and mu term, they are separated. So what we can do, the t term is constant, right? So we know the t term given the previous estimation. We can calculate the t term. So the tau term can be maximized like separately, and then the second term, the second one will be the mu term plus the covariance term. They can be maximized separately as well. So the M step, what we are trying to do is we are trying to maximize tau term from the log of tau, and then we are going to maximize the mu and sigma term from this part. So the minus 1/2 log sigma determinant of sigma j minus this quadratic form here. So here let's maximize the tau term. So tau term, we know the tau 2 is equal to 1 minus tau 2. So tau 2 equals to 1 minus tau 1. So we maximize the tau term, and so by taking the derivative of tau, we can easily get this estimation. It's easy derivative calculation. So what about the mu term and sigma term? So the mu term and sigma term is a little bit complicated, but it's doable. Here we're gonna use some more advanced knowledge. We're gonna use matrix calculus. So I'll explain a little bit. We don't need to introduce the whole matrix calculus, but we're gonna use some of those knowledge that is necessary to prove our result here. So now we already have the formula of calculating the tau given the previous t. We can calculate the next tau term, and then we need to find the next mu term and the next sigma term, t plus 1 term. So to derive the formula for mu, we're gonna use a formula which is the partial derivative of vector the transform tau, because the quadratic form of the partial derivative of w is actually 2 times the matrix A times the vector w, where A is symmetric. Well, A is symmetric is our normal thing, because our normal random variable, the covariance is symmetric. So we take the partial derivative of mu1 with respect to q, and by this formula we get this term, the minus 1 over t and 1 over 2 log of we get this term mu1, this quadratic form. We take the derivative and let it equal to 0. We get the 2 cancel out with the 1 over 2, and t term is coming into the sum, this quadratic form, and then that will become sigma 1 inverse of sigma 1 times the vector xi minus mu1. So that's our form. That's how we get it using this formula, and we get the mu1. Same for mu2. Here we are calculating mu1, but same for mu2. So how do we get this term? How do we calculate that? Well, there's no secret of calculating this one. There's no secret. You just expand the definitions of matrix multiplication, and then you just take the derivative. You can, if you don't make any mistakes, you can easily figure out that this is actually 2a times w. I'll leave it to you guys. If you want to have a proof, then let me know. I can create one in a separate video. So now we need to find the formula for the next iteration for sigma t plus 1. So next estimation for sigma. Here it will be a little bit more complex. So we're going to use a couple of formulas, equations. The first one is invariant under cyclic permutation, which is of traces. So the trace of matrix multiplication A, B, C, if we take the cyclic mutation, so we move the C to the front, so that will be a C times AB. So the trace of ABC is equal to trace of CAB, which equals to trace of BCA. So that's one thing. This is also easily provable by expanding the definition of traces. I'll leave it to you guys. Same thing, if you want me to prove it, just let me know. I can create a video for that. Derivative of trace. So now there will be something interesting. This is the partial derivative of a matrix. So here A is a matrix. We're taking the partial derivative of a trace with respect to a matrix. So that definition, so the result of this derivative is actually a matrix. So the definition of the derivative of matrix is actually taking the derivative of each term in the matrix, and that will become the whole result of the matrix. So here each term of this derivative is actually, so the I row j column term is this one. This is the single element in this partial derivative of A, and we separate that. So we take the definition of traces. That will be this sum of two sum going through the elements in B and element in A. So that will be the k column. K row L column of B times L column L row K column of A. If you take that derivative of Aij, you see that only when K equals to I and L equal to J, other terms will become 0, because other terms is constant with respect to Aij. So that will become the term Bji, which is, we proved that this is just a transform of matrix B. So next we're gonna need to to derive the formula for sigma function, a sigma matrix is what is the derivative of a log determinant. You see here when we try to maximize this, take the partial derivative of the sigma 1, we actually need to take the partial derivative of the log of the determinant of sigma 1 here. So we need to know how to do that, and the result of this one is just A inverse transform. So to establish the result, know that the log of matrix determinant of A is actually 1 over the determinant of A times the partial derivative of Aij of determinant of A. And recall the formula for the matrix inverse. The inverse of a matrix A is 1 over determinant of A times the cofactor matrix transform. Therefore, the A inverse T is actually 1 over A determinant times the cofactor matrix C. So if you compare these two, you'll notice that all we need to prove is the partial derivative of Aij with respect to A equal to C. So if we can prove that, then we prove the whole thing here. Right? So, however, determinant of A is actually is by the definition is this one. M is the minor of A. For those who don't know, the minor of Ij is the determinant of A, removing the I row, moving the J column, and take the determinant of the rest of the matrix at matrix terms. So how do we do that? So it's just pure computation. So the partial derivative determinant of A of Aij is by this definition, we expand it. Now that will be simply minus 1 minus I power of I plus j times Mij. Right? We just proved it. So this is what? This is exactly the cofactor C, the cofactor matrix C. So now we prove the formula partial derivative of log of determinant of A over part of A is A inverse of transform. The last formula we're gonna need is the determinant of an inverse is the inverse of the determinant. I won't be proving that. You can easily find, if you don't know that, you can easily find it online. So now we have all the formulas we need to derive the estimate, the formula for sigma matrix. So let's go to the terms we need to maximize. So see here, we need to maximize the whole term here from removing the log tau j, removing the last constant d over 2 log 2 pi, remove this. So this is the term we need to maximize. Remember, I included the minus sign. So the whole term here we need to maximize. So we're gonna take the derivative of sigma j of this term and then take the derivative sigma j of this quadratic form. So the quadratic form here, so the quadratic form xi minus mu times the sigma j inverse times xi minus mu is similar to the form of here. This is the one that we just. This is one of the. So this is, we need to take the derivative of that, but this is a scalar, right? So this is a quadratic function. This is a scalar, and a scalar is the same of the trace, right? So the trace of this scalar is the scalar itself. And so that will be the trace of x transform t, a times x, and that will be by this rule, trace of this rule, we are gonna move the last x to the front, cycle move, and then take the derivative of a, and by this formula we know this is just the transform of x xt, and the transform of that, because it's symmetric, it's just itself. Now we get so we take the derivative of q with respect to sigma 1 inverse. We take that. So here the log term, we are taking the inverse of minus the inverse of sigma 1 and this one minus the trace of this, well, the quadratic form, minus the partial derivative of the quadratic form, which is a scalar, so it's same for trace. If we apply those formulas we have for taking the derivative of trace, we get the whole term, we get the result here. And by moving around those terms, we can get the sigma 1 t plus 1 term equals to this. This is what we get from here. Same for sigma 2. Same for sigma 2. So now we have all the formulas from estimations for tau plus 1, tau the term next iteration t plus 1, to the mu 1, mu 2 for the next iteration t plus 1, and the covariance matrix for t plus 1. So we got all those terms, the formulas. Now we can calculate by the EM algorithm. Now we know how to calculate the m step. So the m step here, now we can calculate the whole theta vector. And then with iteration, and we set an error, epsilon, any reasonable error term. As long as the q becomes smaller than this error term, we will stop, and that will be the theta estimation we can use for defining the point estimates of the PDF for the x. So the EM algorithm is one last thing we haven't solved. That is the initial value of theta. The whole algorithm works if we have initial algorithm of theta. This could be done with k-mean algorithm for those who know that. And using k-means, we can have a pretty good initial estimation for theta, and then to kickstart the whole EM algorithm. You can also give your intuitive guess of those values, and then to gradually convert to the right maximum value. But there is some drawbacks of EM algorithm. As you can see, it could be easily fall into a local maximum value of Q rather than the global maximum value. But in most cases, it shouldn't, especially normal. So we have to be very careful, and there's some limitations of EM algorithm as well. And that's it. Now we have everything, and we can write it in code to set up a formula, to set up a code to automate the whole calculation for model, building a model for analyzing data. And that's it. Thank you, everyone. If you like it, smash the like button and subscribe to the channel. remember to click on the bell so you get a notification for the next video. Thank you everyone.